In this video, we'll take a look at a few special matrices that often pop up in either theoretical or applied situations. So these are matrices that have some special properties that are worthy of our attention, right? And the first group, and it's really a group of two, but so there's the concept of triangular matrices, right? And the word triangular that came up earlier when we were looking at linear systems. Before we got to the precision of an echelon form, we said, hey, if we could get our system in a triangular form, then we can use back substitution to solve, right? Now we're just going to define precisely, what we mean by triangular. So just as how we have a very precise definition for an echelon form, we're going to have a similarly precise definition for triangular form. Now, it's not going to have as many requirements, and you'll see why. Right? Now, there are two ways that a matrix can be triangular, right? And the first one, we refer to it as being an upper triangular matrix. So let's define what that is. An upper triangular matrix, let's call it A, is such that A is a matrix with entries, big shocker there, and it has this particular property that the Aij must be equal to 0 whenever I is greater than j, right? So that's what we mean by upper triangular. So what I'm going to do is write it down like in the expanded form with the A1, 1, and so forth, and then show you exactly what this requirement means. And then easy by observation, we'll be able to look and tell if a matrix is upper triangular or not, right? So let's write this sort of in the expanded form and see what happens. So if your I is greater than j, then it means you're further down than you are across. This is saying that your row index is greater than your column index, right? So remember, the entries on the main diagonal, that's where your I is equal to j. So it's like 1 1 2 2 3 3, etc. Now I don't know how big the matrix is, right? So I'm just going to kind of leave it open-ended like that, and then down to like a and n. But even then, I'm going to leave it out, right? And it doesn't say it doesn't give any requirement for when I is equal to j. So basically, we can leave this as arbitrary. Like it could be any entry. Similarly, it doesn't give any requirement when I is less than j. So in other words, over here, again, it could be pretty much any numbers that we want, right? Dot, dot, dot. But what this is saying is, again, whenever you go further down than you go to the right, you have to have entries that are 0. So you have to have a 0 in that position, and in that position, and in that position, all the way down. And similarly here, right? Because once I go down in this column, yeah, my I, because I'll be in row 3 but still in column 2, so my I will exceed j, and by definition there has to be a 0 in that position. And then similarly here, right? And like this. So the upper, what the upper is referring to is that on And above the main diagonal, you can have any numbers that you want, including 0, right? You could have a 0 over here. But for sure, everything below the main diagonal has to be equal to 0, right? So, and this is kind of what we did when we were trying to get our systems in a in a triangular form. We wanted zeros in these positions, right? So now we have a special name for a matrix like that. It is called upper triangular. So here are some concrete examples that might help, right? So let's say you have just a 2 by 2 matrix. If I have something like this with a 0 right there, this is upper triangular, right? Because there's really just one entry that is required to be 0, and it's that entry in the 2, 1 position. All right, so that one's upper triangular. Let's just kind of, give a bigger example so you can see the pattern. So now let's say I have -1, 0, 8, 5, 6, 4. So I have these entries here. And remember, any numbers are, all numbers are allowed on the main diagonal and above the main diagonal. But below, for it to be upper triangular, then I have to have my little triangle of zeros right there, right? So this one is also upper triangular. All right. Now, there is another type of triangular matrix, and that's the lower triangular matrix. And all I have to do is switch this inequality around and keep everything the same, right? So let's write that down and then again do some examples. So a lower triangular matrix, again, let's call it A, is such that our entries now, Aij, the requirement is that Aij is equal to 0 whenever your I is less than j. So if your j is bigger than your I, then it means you are further to the right than you are down or to the bottom, right? So this one, I won't write the generic kind of expanded form. I'll just go to specific examples. And basically, so let me use these examples to show you a nice relationship between upper and lower triangular matrices using one of our special matrix operations. So for instance, if I took the A that I have right here and I took its transpose, remember what the transpose does? It takes rows and makes them into corresponding columns. So row 1 that now goes across, if I take its transpose, if I take the transpose of that matrix, I'll have 1, 3 that way. And then the second row becomes the second column. Now look where that 0 is now located. That 0 is now above the main diagonal. And so in a lower triangular matrix, you're allowed to have any numbers on or below the main diagonal, but everything above now has to be 0. So this one is lower triangular. And I'm just using the transpose as a way to kind of give you a specific relationship between the upper and the lower, right? I didn't have to state it in terms of the transpose. I could have just written another one down, but I thought that would be a good way to not only remind you of the transpose, but show you a nice direct relationship between upper and lower triangular matrices. right? And similarly, if I took the transpose of B, that would give me an example of a 3 by 3 lower triangular matrix. So B transpose, again, I always, for whatever reason, I like taking rows and making them into columns. So that first row becomes the first column. That second row becomes the second column. And then the third row becomes the third column. And again, part of the reason why I'm putting a 0 on the main diagonal is because on and below, you're allowed to have any number, including 0. But what for sure is required is that above has to be 0. It doesn't say that on and below the main diagonal has to be non-zero. No, it doesn't say anything about it. The only thing the definition states is what has to happen for the entries that are above the main diagonal. So this is also lower. Right? So two simple concepts, upper and lower. Now the upper, we saw how we could utilize that form before we got to the echelon forms. Utilize a triangular form and a back substitution in order to solve a linear system. Well, technically speaking, there is no rule that we had to have the triangle below the main diagonal. We could easily, and I say easily, we could easily have eliminated entries above and started with the top row and used what's called forward substitution. And again, when you really analyze the algorithms that we're talking about now and writing the programs that would implement these algorithms, yeah, you realize that, hey, why do I have to work backwards? Why can't I think about it forwards? And there are some algorithms that kind of blend both approaches. So again, that's beyond our the scope of our course. But I just want to show you, and I like to point these things out in that it's another instance where if you get too fixed in a particular mindset, you lose more general, more important patterns, right? In other words, you don't want to be closed-minded. You don't want to just say, okay, I'm always going to do this. I mean, it's nice to have a process in mind, but also it's equally important to be open-minded, right? So those are triangular matrices. Now, the next group, uh, uh, these are called diagonal matrices, right? And a diagonal matrix, so now let me define it for you. So a diagonal matrix A, so A, in other words, this is just saying one of them, not the matrix A, but a diagonal matrix A is such that, so let me write this condition down and see if we can figure out what it means. Aij such that Aij is equal to 0 whenever I is not equal to j. So if you think about what that is saying, right? In the upper triangular matrix, the definition stated that I had to be greater than j. In the lower triangular matrix, the definition says that I would have to be less than j. And now the diagonal matrix is saying that in order for 0 entries must appear in rows and columns where I is not equal to j. Well, what that means is it means that a diagonal matrix is both upper and lower triangular. And that's exactly another way that you can define a diagonal matrix. You can say that these matrices are both upper and lower triangular, right? So that means we have to have now triangles above the main diagonal and below the main diagonal, all right? And in some sense, we've kind of seen that, and I'm just going to say a little bit more before I again point out that we've seen this concept before, but now we're just defining it in a more general way. So again, here are just a couple examples. I'm not going to write it down in that um, uh, generic random uh, expanded form. But let's say, so here's a 2 by 2 example of a diagonal matrix, right? Above the main diagonal we have a 0, below the main diagonal we have a 0, and again we can have anything on the main diagonal. In fact, the 0 matrix, like the 2 by 2 0 matrix that looks like this, that also is a diagonal matrix. It just so happens that not only do we have zeros above and below, we happen to have it on as well. Remember, these definitions are not saying that these are the only entries that can be 0. What it's saying is that these are the entries that must be 0. The other ones could be 0, or they could be non-zero, right? And then here is like a 3 by 3 example, something like that, right? And that's so these are all of these are diagonal matrices, right? And it turns out that these matrices, they're easier to multiply, and there are lots of other operations that that are more easily accomplished if we do it or do those operations with diagonal matrices. Now, here's an interesting thing about diagonal matrices. And so for instance, let's say I took this A and I took its transpose. Look at what's going to happen. That first row, that 2, 0, becomes my first column. And then my second row, 0, 4, becomes my second column, 0, 4. But look at that. It's the same. And obviously, if I do that with the 0 matrix, that will happen as well. I won't write that one down. But look at the transpose of C. If I took the transpose of that matrix, then again, that first row becomes the first column, and there is no change. Second row, 0, 5, 0, becomes the second column, 0, 5, 0. Again, no change. And then finally, the third row, the 0, 0, negative 8, becomes a 0, 0, negative 8. And again, no change, right? Now, the diagonal matrices, they have this particular property. Other matrices have this property, and matrices whose transpose is the same as the original matrix, those matrices are said to be symmetric matrices, right? So that's another type. So I wanted you to kind of see this particular property, right? It always works for diagonal, but it works for other special types as well. So the next type that I want to mention, these are symmetric matrices, and this is the definition. A matrix A is symmetric if and only if its transpose is equal to itself, right? So let's kind of think about this. So if A is m by n, then we know that A transpose is n by m, right? We saw this. This is one of the properties, or one of the natural consequences, actually, of the definition of the transpose, right? But we're saying that these two are equal. But go back to our definition of equal matrices. Two matrices are equal if they have the same dimension and their corresponding entries are equal. So the only way, so for starters, right, the only types of matrices that can be symmetric, right, are the ones where m is equal to n, right? So that means, so this implies only square matrices can be symmetric, right? So putting this all together, right, this is the definition of the transpose. The definition that we have for equal matrices is that their dimensions have to be the same. So that means whatever is here would have to be equal to this, and similarly, whatever is here is equal to this. So if the row and column values are equal, if you have the same number of rows or columns, then the conclusion is that A is n by n, meaning it is square, right? So in terms of the dimension now, only square matrices could possibly be symmetric. But also, we can say a little bit more about not just the dimension of the matrix, but the entries in the matrix. The other thing that is a natural consequence of these definitions is this: the entries that are, so for instance, so let me write it like this. So if I start with my matrix A and I take the transpose, what I would be doing is doing this. So it would be A, J, I, right? So what this is saying is that for symmetric matrices, the entry that's in row I and column J must be the same as the entry that's in row J, column I. Otherwise, they wouldn't be equal, and otherwise we wouldn't have this definition, right? So now with those two in mind, here are some examples of symmetric matrices, right? So I can put anything on the main diagonal that I want, right? But for instance, if I put a 4 here in row 2, column 1, I have to put a 4 here in row 1, column 2. And if I put an 8 here in row 3, column 1, then I have to put an 8 here in row 1, column 3. And if I put a 7 here, I have to put a 7 here. So what happens is, in symmetric matrices, there is a symmetry with respect to the main diagonal. It's like what the upper this triangle here is a mirror image of this triangular here. There is the 4, like that. There is the 7, and then there is the 8, right? So that's how you can just look and tell. You can have any numbers on the main diagonal because those don't change position. But in order for me to guarantee that when I take the transpose, I get back the original, and this is what would happen here, I have to ensure this kind of symmetry. And this is why it worked in the diagonal matrix. Because in the diagonal matrix, these matrices, these entries have to be 0. So they're already the same. So when I flip, or when I do my row and column swap, I end up with the same entries in those positions to begin with. So if I take the transpose of this, it's going to be the original. So this is an example of a symmetric matrix. Right? So this is symmetric. Now, it turns out there is another type that probably doesn't show up as much in at least this level of linear algebra, but there's a concept of skew symmetric matrices. So skew symmetric. And I'll just write down the definition, and then we'll see like what has to be true based on that definition. So skew symmetric matrix. So a matrix A is skew, and sometimes it is hyphenated. A skew symmetric matrix if and only if when you take the transpose of it, you get the negative of what you started with, right? So, again, these can only be square matrices because we know multiplying by a scalar, which is this is our -1 scalar, is not going to affect the dimension, right? So again, so right away, it implies that A is n by n. The other thing too is if I write this down, so this is saying if I take the transpose of this matrix, I am going to get the, so let me write it down. So the transpose of this, the entries would be swapped like this, right? And then I'm saying this is also equal to the negative of the original. So here are the entries in the transpose, and here are the entries in the negative of A. And we're saying that these have to be equal. So now you see what has to happen. It's not going to be the same entries in those like mirrored positions. It's going to be the opposite entry, right? So if I put a 5 in one of those mirrored positions, I'll have to put a -5 in its mirrored opposite, right? The other thing too is, think about it. This is true for all ij. So what happens if I is equal to j, so what the elements that are on the main diagonal, what do they have to look like? Well, if I replace all the j's with i's, this implies that the entries in the II position, like 1, 1, 2, 2, etc., have to be equal to the negative of those same entries, right? Well, what number is the same with or without a negative in front of it? Well, I mean, let's look at it. So this is saying, for instance, that AII has to be equal to the negative of AII. Well, if I add AII to both sides, I have 2AII is equal to 0. So this implies that the entries on the main diagonal would have to be equal to 0. So we know what skew symmetric matrices now look like, right? So I can only put zeros on the main diagonal, and then I have to put the opposite of entries in those mirrored positions. So here's an example of a 3 by 3 skew symmetric matrix. 0, 0, 0 has to be there. If I put a 2 here, I have to put a -2 here. If I put a 10 here, I have to put a -10 here. If I put an 8 here, I have to put a -8 there. And what happens is, if you take the transpose of this, so let's say this is our A, let's write down the two operations that have to be equal to each other. Let's write down the transpose. The transpose, take the first row, make it the first column. Second row becomes second column. Third row becomes third column. So that's the transpose. Let's write down the negative of this matrix. So the negative of A, doing our scalar multiplication, take -1 and distribute it to all the entries here. And look at what's going to happen. Right? If we distribute that -1, you can just see everything changing over, except on the main diagonal stays the same, and these two are now equal, right? So therefore A transpose is equal to -A, so therefore this matrix is skew symmetric, right? So it's just a matter of there's certain patterns that are important, and we saw the importance of the triangular forms. Specifically for us, it was the upper triangular forms, and we use that along with back substitution, right? And there are other instances where symmetry and skew symmetry will be important. Maybe the skew symmetry not quite as much, but it's just showing you that there are some matrices out there with these special characteristics that make them easily identifiable. And then for instance, there are some times where you know exactly what property you need your matrix to have in order for something else to work, right? So it's just giving you these definitions and making sure that we can recognize when these properties are available. All right? See you in the next video.